Hi, this is Mr. Anderson, and today we're trying to wrap up our question about how are atoms different. And our last big topic to discuss are electrons. So on the screen we have a picture. The picture shows us the nucleus, where we have the protons with a positive charge, and the neutrons with a neutral charge, the tan-colored particle in the picture. But outside of the nucleus, we have these electrons. And these electrons are really important because electron movement causes chemical reactions. Oh, chemical reactions sound like they're pretty important in chemistry, right? So let's take a look at how all this works. Now, before we go too far, we need to refresh ourselves on parts of the periodic table. Remember, when we were studying this, we figured out that the top part of it is called the atomic number, and it's made of protons with a positive charge. Right? Remember, this is the identity of an atom. Any atom of carbon would have to have 6 protons. But if this is on the periodic table, this is electrically neutral. So we know, since it's neutral, if there are 6 protons, there are also 6 electrons. And we've also learned this bottom number here is called the atomic mass. And the atomic mass is made up of protons and neutrons from the nucleus. So remember that protons and neutrons are what make up the mass of the atom. The electrons do have mass, but they're so small. Their mass really doesn't make any difference. So today, we're going to feature the electrons. And when we're talking electrons, we don't care about the mass. It's all about the charges. And that's our focus now. So you may recognize this. Here's an atom of boron, and when we go through it, we know that the atomic number, the smallest number in the box, tells us that there are 5 protons. We also know that since this atom's from the periodic table, it's neutral, so if there are 5 positive charges in the protons, there also have to be 5 negative charges from the electrons. To figure out the neutrons, we take the largest number, the atomic mass. We subtract it by our atomic number. So we have 11 subtracted by 5. And that tells us that there are 6 neutrons. Okay, so now that I know this, I'm going to take a moment and fill my atom model here with the protons and neutrons and the electrons. Okay, so I have all my particles. Remember, particles are protons, electrons, and neutrons. All my particles are moved into place. I have my 5 protons in the nucleus and my 6 neutrons in the nucleus. And I also have my electrons set up. Now you've probably noticed these other words that I have on the screen. The first one we're going to talk about is the orbital or energy level. So the orbital or energy level are these black circles here for the atom. Each one of these is an orbital or energy level. Right? And we have this extra box on the screen, and in this box, let's talk about this fact that each orbital can only hold a certain number of electrons. And the reason for that is the charges of the electrons. So each of these black rings is an orbital energy level, and I think we've even mentioned before that they're called shells too. And each of these can only hold a certain number of electrons because electrons have the same charge. And just like magnets, if you've ever taken 2 magnets and tried to push them together, you've noticed they push away. Well, electrons are very similar. their same charges repel them away from each other, so you can only have so many of them in a certain space. And through a lot of experimentation, chemists have actually figured out what those are. And before we leave this screen, I want to make special mention of valence electrons. Valence electrons are particular electrons in this model. The valence electrons, valence means outside. Valence electrons refers to the outer ring, the outer orbital of the atom. So, in this atom, there are 2 electrons on the first orbital and 5 on the second. That's very important because these valence electrons are the ones that would do any kind of chemical reaction to change this atom to bond with others. So, these outer electrons are really important in determining if something is an atom versus what's called a compound. Let's take a quick look at what the differences are. So, when we're talking about an atom, we're talking about protons, neutrons, and electrons organized in a specific way. You can have more than one of the same type of atom joined together. So in our picture here, we have helium and we have 2 oxygens joined together. We could have 2, or we could have a bunch of those. That normally doesn't really happen with gases, but metals do. So you may have seen a big chunk of metal before. Well, that's millions, maybe more than that, of the same atom joined together. So when you have that, like in a huge block of, say, silver or gold or aluminum, or you've probably seen a zinc before, like a zinc screw, right? That's an element. It's the same type of atom joined together. Right? And when we say joined, another word for that in chemistry is at the bottom of our screen called a bond. And a bond is when the electrical charges between atoms and the nucleus of an atom are causing them to stay together. So when the same types of atoms are staying together, we call that an element. But when 2 or more different atoms, so in our picture we have oxygen and hydrogen, when their electrons and the nucleus of those atoms form an electrical relationship, a bond, that makes them a compound because they're different atoms bonded together. To figure out how this works, we need to know some of the basics. And one of the basics we need to understand is this arrangement of electrons. So this is one of those things in chemistry you're going to have to memorize. So it took a lot of experimentation to figure this out by chemists, but they figured out that the orbital closest to the nucleus can hold 2 electrons. After, I put these arrows here, so after it is full, after it has 2 electrons, then electrons move out to the next energy level. And this energy level can hold up to 8 electrons. So it doesn't have to have 8. It can hold up to 8 electrons. That's an important difference. Now this energy level, these energy levels have to be full before any electrons will move to the next orbital. So the energy level or orbital closest to the nucleus has to have 2 electrons. Then electrons will go to the second orbital. After it's full at 8 electrons, then electrons will begin moving out to the third orbital. And this orbital, like the second, can actually hold up to 8 electrons. after the third orbital is full, electrons can go out to the fourth orbital. The fourth orbital can hold up to 18 electrons. So our pattern is 2, 8, 8, 18. All right, so what we're going to do is we're going to use this knowledge to make a simple type of model called a Bohr model in chemistry. Niels Bohr was one of the scientists credited with figuring out all this electron movement. If you notice on our picture, though, our electron models are a little different than last time. We're going to simplify this a bit. So, in this atom model, I have lithium on our screen. Let's go ahead and fill out the number of protons, electrons, and neutrons for lithium. Go ahead and pause the video, fill it out, and then we'll check your work. Okay, so you found that there are 3 protons from the atomic number. You know that on the periodic table, protons and electrons are the same. And you took 6.9, which rounds to an atomic mass of 7, subtracted by the atomic number of 3, and that gave you 4 neutrons. All right, so one of the things that's different this week in our Bohr model we're going to do, we're not going to worry about pulling over, dragging a bunch of circles into place. In a Bohr model, we'll simply write the number of protons and neutrons in a nucleus. We know there are 3 protons and there are 4 neutrons. And now what we're really going to focus on are the electrons in the orbitals. So we have 4 green boxes up here. We'll pull down the number we need. So we know that in the first energy level, also called an orbital or a shell, that there are 2 electrons. And now we have to be careful with our math. We have to check. All right, so there are 3 protons. We already have 2 electrons. That means we need 1 more to balance out with 3. So we'll pull 1 more box over here. We're going to have 1 electron. And this 1 electron is our valence orbital. It's our valence orbital because it holds the valence electrons, the outermost electrons in this model. This is the electron that would interact with other atoms to form chemical bonds. This is the electron that could change lithium from being an atom to a compound. And we can check our work when we're talking about our electron models using the periodic table. So let me show you a little trick to check your work. You can check to see if you have your electrons correct in your Bohr models. So on your screen, give you a moment to adjust yourself, you have the periodic table. So here's a model of the periodic table, and this is just a snippet of the periodic table. It's not the whole thing. It's a small part of it. And let's find lithium. I'll help you. So lithium is right here on the periodic table. It's in the first column. Columns go down. The first 3 columns on our periodic table, for the most part, show metals. This pinkish streak in the middle is the transition metals from the periodic table. I did not copy this part down because it has its own set of rules that we're not going to be discussing in our class. For us, though, if you notice up top in the blue on our periodic table, there are Roman numerals. Let's read over them real quick. So, the first one is 1, 2, 3 little marks means 3. The V means 5. So here where we have a 1 before a V, we have to subtract 1 from a V. V is 5. 1 minus 5 is 4 in Roman numerals. Likewise, after 5, we have a V and a 1 after that. So that means we add a 1 to 5. So this is 6. We have 7, and last is 8. Right? So these Roman numerals are a shortcut for chemists to check their work. They tell them how many valence electrons an atom should have. So here we see lithium is in the column with 1. So we can go back to our work and we can check, do we have 1 valence electron? We do. So that's a great sign that we have our electrons shown correctly in the model. Okay, so at this point you're going to do some practice problems, and then afterwards check out our next video to check your work. See you later.